Okay, so this is the second part of the problem. So we addressed the pre-flashover stage, and now we're going to be looking into this sort of full compartment filled up with smoke, which is a post-flashover stage. Now, this part is a little bit of a historical account, because this is the other problem that we normally deal with fire. So again, I'm going to take the example of the very, very, very simple approach, okay, and then move into the direction of the more complex approaches to the problem. But in this particular case, the interesting thing is that it pertains the behavior of a structure, of a building, okay? So it is dominated by the time or the period of time where you actually needed to answer the question. So when we introduce steel into the construction industry, people recognized that they could start building very tall buildings, and in building in a cheap, effective, and rapid way. So immediately there was this tendency to try to construct very, very tall buildings, which were steel frames, but the problem was that steel, as it heats up, it loses all its mechanical properties. And because it loses all its mechanical properties, and it's susceptible to collapse. And you don't want very tall buildings collapsing because of fires, okay? Now, when did this happen? So when did we start building tall buildings, for example, in the United States? More or less 100 years ago? Yeah, 1900s, no? So basically, if you look at Sullivan and all the architects in Chicago, you're talking 1896, 1904, 1906. When was the Reynolds number? Lord Reynolds, more or less what period of time it is? Yeah, it's 1920s, more or less. So we had a problem that we needed to solve before we even had the basic knowledge of fluid mechanics. Semenov, didn't get his Nobel Prize for ignition until 1936. So we were beginning to understand ignition in 1936. Okay? Nevertheless, this problem appeared in 1870, 1880. So the real problem here is that we ended up coming up with a solution. And that solution was cemented in the 1920s. There's a famous paper by a guy called Ingberg in 1926, where he presented the solution to the problem. Now, with hindsight and knowing a lot more about the physics of this, we recognize that that solution was completely wrong, okay? But we had already been using it for 50 years. Now, how do you break from a solution that has enabled you to construct half of New York? Are you going to admit that you were going to do it, that you were doing it wrong? So it's pretty tricky, no? And so in a way, this analysis, that aims at being rational, is being presented, in competition against something that has absolutely no physical basis, okay? And that stains the whole process and puts us in a hybrid space that is a little bit bizarre. Now, this happens a lot in fire because obviously, fire problems have existed way before we had the knowledge to solve them, okay? And many times, so you wonder, it's like, why are we doing this, okay? And then you realize, well, because we were doing it since 1810, and nobody wants to change because they've already got used to doing things in a certain way. So anyway, as I'm going through this, I'm going to put some historical components into this so you get a little bit of a sense of what are we dealing with. Now, the idea is that we need to assess structural behavior. So this is a Museum of the Future in Dubai. And so I worked in the design of this building. And it is a fascinating problem of optimizing a structural design that is extraordinarily complex and at the same time making it fire safe using tools that belong to the 19th century. Okay? And so this is the kind of things that we are looking into, and this is the problem that we were trying to address in the late 19th century. So this is a fire in a factory, And this is a timber beam, and this is the modern steel beams that were supported by that timber beam. So in essence, as the fire progressed, the timber charred, so its degradation, its loss of cross-section is extraordinarily slow. But the steel is being heated up by radiative and convective heat transfer very rapidly, and very rapidly loses its mechanical properties, and you see it how it's hanging off the timber beam as if it was a pasta. No? So in essence, this is a problem that we were facing, and this is a problem of the 1850s, 1860s. So the approach that is used is called fire resistance, and it's due to who formalized it is Ingberg, and it was in 1928. Now, interestingly enough, you can see this is the first attempt that fire people had at being scientific. This is page 1, volume 1 of the National Fire Protection Association journal. Okay? So this is our first attempt as fire people to try to be scientific in one way or another. Now, the testing data is very, very, very sophisticated, and you can see it here. This poor man is trying to throw timber as fast as he can into this box to try to make sure that he gets the hottest possible temperature. Okay? So as a result, he ran this experiment many, 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 many times, and Ingberg collected about 40 years of data that had been collected mostly in the United Kingdom and in the United States, and basically tried to establish a worst-case scenario. So what they did was they took all the data, and instead of trying to understand what was going on, all they did is pile all the data and construct a mathematical function that served as the envelope. Okay? Now, that mathematical function is not a fire. It's just an envelope that basically is above all the data that you have available. Okay? So this envelope, because it's not physical and it's a continuous mathematical function, it just simply continues to progress into temperatures that become completely unphysical. Okay? Now, but you can actually say, given the data available at the time, this fire is the worst case scenario. A fire cannot be hotter than that. So if I reproduce that temperature in a furnace or in an oven, and I put my structural element and it doesn't fail, okay, then I can argue with the knowledge that they had at the time that if it doesn't fail for this red curve, it will never fail. Okay? That was the argument. Now, the other variable in heating is time. And they recognized that as a function of how much fuel they threw in there, the fire will last either a short period of time or a long period of time. The more fuel, the longer the fire, the longer the heating period. So the insurance companies in the US went around measuring the quantity of fuel that different buildings had. So they came up with an average quantity for offices, an average quantity for residential buildings, average quantity for hospitals, and on the basis of that average quantity, they looked and said, oh, for 60 kilograms per meter square on average, okay, the fires last about 30 minutes. Okay? For 80, they last about 45 minutes. And they set up a criteria saying, okay, if the fire can only last 30 minutes for a residential building, then I'm going to heat my structural element for 30 minutes because that's the longest possible duration that that fire can have. So now I'm heating with the worst possible curve for the longest possible duration, which is burnout, all the consumption of the fuel. Okay? So in essence, if I heat my structural element for those conditions and it doesn't fail, it will never fail. Okay? So that was the principle. Okay? Now, obviously, it has no physical basis. It is just purely a mathematical construct. But nevertheless, the curve defined by enveloping all the fires gives me the worst case scenario, and the required rating is defined by the total fuel consumption. So this is why when you design a residential building, they say your structural elements shall be designed to 30 minutes fire resistance. Because residential buildings are expected to have a certain amount of fuel, the time for burnout is supposed to be 30 minutes, and therefore they will be tested against this curve, okay, for 30 minutes. If you're designing an office building, then they will say 60 minutes, okay? And basically you will design for 60 minutes, and it goes on multiples of 30, okay? Now, if you have a very, 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 very tall building in the center of Manhattan, you are designing the World Trade Center, okay? Then you say 4 hours. Why do you say 4 hours? Because I know this is not so physical, so let's multiply everything by 4. Yeah, so it's just a safety factor, okay? So you make it super conservative. So the reason why buildings don't fall down from the sky today is not because they're properly designed, but it is because they're so conservative that effectively, as a result, you have these extraordinarily robust buildings. The problem is that because you're not designing them in a physical way, then when odd things happen, like 9/11, then you realize that you missed something. And the actual design of the Twin Towers was a design that was extraordinarily vulnerable to fire, okay? So it was a very, very, very simple problem of simply saying rigid column, okay? Rigid core, very lightweight floor. So what happens when you start heating up the lightweight floor? It tries to expand, but it is restrained by two very rigid systems. Remember all the columns? They were one after the other one, so the perimeter columns were super rigid. Okay, so you have this very rigid core, very rigid columns, and you have a very lightweight floor that is trying to expand, and it cannot because it's restrained. So because it cannot expand, it fails and it buckles. The moment it buckles, it hangs. So if it hangs, then it's going to try to pull the columns in with the entire weight of the floor. So the moment it tries to pull the columns in, it's going to create a load on the floor above and the floor below because they're being pulled in, and they start compressing the floor above and the floor below, which are completely lightweight. So they will buckle too, and now you have 3. Okay? Now the 3 now are hanging, and they're bringing the columns further inwards, and they buckle the one above and the one below, and now you have 5, and then you have 7, and then you have 9. And the failure progresses all along the building. Now, if you were in the John Hancock in Chicago, the Sears Tower, or any conventional tall building, you will have a rigid floor every 10 floors or so. The design, you see the braces of the John Hancock? So you have these massive braces, and then 2 rigid floors above and below. So that progression will be arrested at those rigid floors because they won't buckle. In the case of the World Trade Center, it was continuous. So once it started, there was nothing to stop it. Okay? Now, technically speaking, with the fire that you had in World Trade Center, if it would have been only the fire, and it would have been designed properly, any other building, that building would have never come down. So it was just the structural design of the building that actually brought it down. So if you're ever interested, read the NIST report. Well, it has like 1,700 pages, but just the conclusions, you can read the conclusions, okay? And you can see how it works. It's actually very well accepted that this is a failure mechanism, and it was purely due to design. Now, with this kind of method, you will never spot that. You will never spot the interaction between different components because all this is tested just in a furnace, okay? So you will never see how all these things are interacting and how you can create massive loads just purely with thermal expansion that is restrained, that effectively creates a buckling process and brings the whole system down. So this is unphysical, but it has existed for 100 years. So the Burj Khalifa, as well as a residential home, are designed under this principle, okay? And it has no physical basis. So the final argument of this is that if you box the fire in one room, then everything around it is cold, and because it's cold, it's much stronger than the elements that are being heated up. So the loads can be redistributed into all the different systems, which basically means that you can test one single element, and if that single element doesn't fail, you know that everything else around it will not fail. Because most structural systems are completely redundant. If you look at this, structural systems are indeterminate redundant structures. So you always have multiple paths for the loads, okay? So in essence, if all the different paths are stronger than the weakest elements, you can take failure of a single element and then consider that as your failure mode. Nothing will fail before that, okay? So in essence, then you can do this, put it in a furnace. This is a typical furnace on which we test structural elements. Make the furnace follow the standard temperature time curve, and then you're going to introduce your structural element. If it's steel, these are the material properties of steel, and what we're going to say is that when we lose 50% of the capacity of steel, which is about 500 degrees, then the steel fails. So you put your structural element in the furnace, you let it heat up, and then you take the failure temperature, and in this case, this will fail at about 40 minutes, and for conservatism, you bring it down to the next 30-minute multiple. So you will say that this structural element will have 30 minutes fire resistance. Now, if you're required to have 30 minutes fire resistance, fine, you can use it unprotected, okay? But if you're in an office building and you're required to have 60 minutes fire resistant, you have to insulate it with fireproofing. So that basically you delay the heating until it exceeds the 60 minutes that you are required to have. Is that okay? So very, very straightforward and simple process that defines a critical temperature as a function of the material properties, and that gives you the fire resistance, and it has to be above the multiple of 30 that corresponds, to the required fire resistance. If you cannot achieve that, then you insulate, and this is typical, sort of shotcrete type vermiculite, fireproofing that you put on buildings. So at the time, we didn't know much. So fire resistance got embedded into the codes and standards, which effectively was used as a representation of the society's responsibility to guarantee safety, okay? Now, it is so conservative in nature for the majority of conventional buildings that you can get a lot of things wrong, and this is not going to fail, okay? So literally, it's truly brute force. Now, the problem is that now we're doing pretty interesting things. And if we're going to start doing, for example, encapsulated timber structures, then we have to start thinking in a slightly different way and a slightly more, sophisticated way, because this is the kind of things that we're trying to do. So this is, for a while, was the tallest timber building in the world, the Brock Commons in Vancouver in Canada. And basically, for example, this building relies entirely on this fire resistance methodology to design the thickness of the plasterboard that is going to protect the timber structure. So now we're still using these very coarse methods, but now we're using it for situations where actually we really need a lot of refinement. And we are allowing, for example, for the timber behind the encapsulation to ignite and char, which effectively is a very tricky thing, no? Because what if it continues to burn on its own? Then you're not designing for burnout anymore. So you are effectively failing to comply with the basic principle of design, is that you want a tall building never to fail. So you have to design for burnout, but if you ignite the timber, then when is it going to stop? And the US, for example, has become really the biggest promoter of tall timber buildings. All the building codes in the US have relaxed completely all the rules in regards to the use of mass timber for tall timber buildings. And as a result, unfortunately, we are going to have a lot of work, because I cannot see any other direction but a complete mess. When you start using this type of very simplistic methods to address very complex problems, then you really have to be a bit careful. So the collapse of the World Trade Center towers emphasized the need for a better analysis, but unfortunately, we didn't learn very much. Now, at some point in history, we had to learn, okay? And this is where rational thinking entered the picture. Now, which are the periods of history where society is most committed to the advancement of science? War. Yeah? So during Second World War, there was a recognition that it was much, much more effective to burn down a town than to simply bomb it. The level of morale deterioration that you could create by creating fires was so much more extreme than just by throwing bombs that an enormous amount of effort, was put into the idea of designing mechanisms to basically create as big of a fire as you could possibly can. Okay? So what happened? At the same time that the Manhattan Project, was occurring, what nobody talks about is that next door there was a similar project, but that project was destined, to develop mechanisms of fire-based destruction. Okay? Now, one of the products of that was napalm. So napalm was a product of that. But what they had done was they had built entire Japanese towns that they were actually trying to destroy by using fire. Now, obviously, this was not only happening in the United States. In the United Kingdom, there was a building research establishment, and they were doing exactly the same, but with German towns. Okay? And there was in Japan, and they were doing exactly the same with American towns. And everybody was trying to look into the idea of how to set everything on fire, and there was an enormous advancement, of the discipline, because effectively they were trying to circumvent a methodology that was so over-dimensioned that it was almost impossible to mess with it. Okay? So it took a lot of effort, but what it actually created was a whole rational framework that basically came in parallel to this existing non-rational methodology. So in Japan, it was Kuno Kawagoe, and in 1958, 13 years after the end of the war, he published all the data that they had collected in the Japanese labs after it was declassified. They published all the data that they had collected in trying to destroy, all this sort of large-scale fires. So Kuno Kawagoe is basically one of the sort of fathers of the discipline of fire safety. And all his data was collected by Philip Thomas, who was the person in the United Kingdom who was doing the same thing at the BRE. And he was actually more of a theoretician. So he created the framework that enabled to analyze all the data that had been produced by Kawagoe, put his additional data, some French data, some Swedish data, all this data together in what is called the CIB report, the Conseil International du Bâtiment, and basically it's an organization in Europe that looks into safety of buildings. And so they created this CIB report where effectively he created all the theoretical framework that served to coalesce all the data that had been created, by Kawagoe in Japan. Now, in Canada, it was Tibor Harmathy, and Tibor Harmathy is really interesting because, as opposed to Philip Thomas, who was dealing with buildings of the nature of buildings that you will find in Europe, in North America, we had much more open floor plans and all sorts of things, and he basically created a framework that enabled to analyze on the basis of risk, how all these variations of compartment dimensions, the introduction of sprinklers, all these other different things could compensate to reduce the hazard or the actual assumed hazard that was occurring in one of these compartments. And finally, in Harvard, there was a Professor Howard Emmons, who was the first person to actually put all this information into a computer model. So it's the first computer model that, that was developed in fire, and is due to Howard Emmons. And basically, as you would imagine, is called FIRST. So very original. And so basically, that's the history. It's all compiled out of war data. And these 4 individuals are considered to be the fathers of proper fire safety engineering. So if you are very prominent and you give the hotel lecture in the Combustion Institute, in fire, in the International Association for Fire Safety Science, you will give the Emmons lecture. If you get the silver medal in the Combustion Institute for the best paper, you will get the Thomas medal, okay? And if you have had a very, very, very long service in the Combustion Institute, you will get the Alfred Egerton medal, or you get the Seldovich medal if it's here or whatever. Here you get the Kawagoe medal, okay? The one who never got a medal was Tibor Harmathy, because everybody disliked what he did because it was not science, it's just risk. You know, it's probability. That was seen as dirty stuff. And so the other 3 looked down on Tibor Harmathy. So there's no medal with Tibor Harmathy until just recently, where the practitioners, the Journal of the National Fire Protection Association, created the Tibor Harmathy medal for the leading junior scientist in fire safety. So in a way, the maverick. Now, funny enough, Tibor Harmathy, was the one who laughed the most, because he ended up frustrated and retiring from fire safety very, very young, and he became a writer of science fiction. And as a writer of science fiction, he became a multimillionaire with a number of very well-known bestsellers. And so anyway, each of them, had their own history, but they created this sort of famous framework that brought us back to the basics. So I showed you this the other day, and basically this is a complicated problem, and we need to find this Q net, okay? And we need to resolve this set of integral differential equations that, again, are intractable. So as a result, we need to understand that this cannot be done, and we have to find something simpler. Now, the great advantage that we have here is that the heating of a solid has a very long characteristic timescale, where the heating of a gas, or the fluctuations in a gas, have a very short characteristic timescale. So averaging the fire is perfectly fine, okay? Because any heat transfer into a brick wall has a timescale of hours. So I don't need to resolve the milliseconds, or even the seconds, or even the minutes. So if I average the fire and treat it as a steady state event, it's okay if what I'm delivering is heat transfer to a solid that takes hours of heating, okay? So that difference in characteristic timescales enables us to simplify the problem, because you can treat the fire as a steady state problem, okay? So this is a formulation that is called the compartment fire, and it pertains typical compartments of the European nature. Okay, so it was designed by Philip Thomas in Europe, and generally old buildings in Europe are very compartmentalized. So effectively what you have is a room, you have the windows, the door, and the bottles of champagne in the top, and basically the size of the room generally very small. These are conventional 1950s buildings in Europe. Now, what Philip Thomas identified is that you have 2 regimes in burning, okay? This regime that he calls regime 2, if you have a big opening, then the fire becomes the pump. So the strongest delta P, the strongest pressure, is created by buoyancy at the position of the fire. And where you get is this extraordinary complex fluid mechanics that brings fresh air at fast velocity, reaches the fire, hits up the ceiling, and is spit out. So this is controlled basically by momentum driven by a buoyant flow, okay? Now, to be able to resolve this problem, you actually need to do CFD. You cannot resolve the problem in an average way because it's a very dynamic problem driven by this fire that is a pump. Now, if you start shrinking the opening in a way that is characteristic of this type of buildings, and you end up with smaller openings, the filling of the room with the smoke is so fast compared to everything else that the diffusion flame displaces itself to the outside, and what you get inside the room, which is what is going to heat up the structure, is literally a box full of black smoke. Okay? And basically the velocities inside the compartment converge to zero, and what you get is a static problem, where you're going to have a box full of hot black smoke that is basically heated up by combustion that happens at the opening. And that opening is going to bring air by hydrostatic pressure and expel flames at the top end. But inside the compartment, your velocities are going to be zero. You can ignore Navier-Stokes and treat the problem as a pure hydrostatic problem, okay? So basically, his argument was most conventional buildings in Europe correspond to regime 1 fires. And we are going to legislate so that all buildings are designed in a way that we can calculate. Okay? So in essence, buildings in Europe continue to be designed under the premise of small openings and small compartments. While in the United States, people started going in this direction, and this is why Harmathy started introducing the management of risk as a function of other protective measurements, okay? So instead of restricting the architecture, what you did is, let's try to find a solution, but that solution is no longer physical. That solution is mechanisms of finding. This is why in the US, sprinklers prevail, while in Europe, you barely see a sprinkler, okay? So in essence, that's where the bifurcation happened. So this is the way a regime 1 fire looks. Basically, air is coming, from the bottom, and the flames are coming out at the top, and everything is happening close to the door, and inside the compartment, you don't get any velocities. Oh, God. So, in essence, the assumptions that Thomas makes is the first thing he says, the heat release rate is defined by the complete consumption of all oxygen at the door. So effectively, your energy released into the compartment is given by the ambient oxygen concentration multiplied by the mass of oxygen that comes in, multiplied by the heat of combustion per kilogram of oxygen consumed. Okay? So the second assumption, this first assumption eliminates the need to define oxygen concentrations because you're consuming all the oxygen that goes in. It eliminates the need to resolve the oxygen transport equation, limits the analysis to scenarios where there is excess fuel availability, which is the regime 1. They assume that the chemistry is fast enough to consume all oxygen transported into the reaction zone, and the control volume acts as a perfectly stirred reactor. In other words, it's all homogeneous, and the energy is distributed in the perfectly stirred reactor. And the heat of combustion is assumed to be an invariant. Okay? Now, the second assumption is that radiative losses through the openings are assumed to be negligible. Now, they measured this, and they showed they were about 3% of the total energy release, so they could be neglected. There are no gas or solid phase temperature spatial distributions within the compartment. In other words, the whole compartment is a single temperature because it's a perfectly stirred reactor, okay? And basically, you can use just an orifice plate approximation to calculate the mass of flow of air entering the compartment at the door. And all velocities within the compartment are negligible. And people derived the constants for different configurations, windows open, doors, and so forth, okay? So this is the framework. And in essence, what you get is, here's your compartment. Now I have only one temperature inside, which is TG max, okay? And so you spit out gases at that temperature. You bring air at ambient temperature. The compartment is all at TG max. You lose heat through the walls, which is what you're interested in. And basically the energy that is accumulated in the compartment is the mass of the control volume times Cp times TG max, okay? And the energy generated is the heat of combustion times the burning rate. But you're not going to calculate it using this expression. Instead, you're going to calculate it using it as a function of the consumption of the oxygen that enters the compartment. So the energy equation basically is the change of the energy in the control volume is equal to the heat generation plus the energy in minus the energy out minus the energy transferred through the walls. The energy in, because it's cold and the mass of the two is the same, mass in has to be equal to mass out, otherwise you increase the pressure. Then the energy in has to be much smaller than the energy out because T ambient is much smaller than the hot gases of the compartment. So you can cancel Q in. You assume it's steady state because the heating of the solid is so much longer than the changes in the compartment. Q in is equal to 0. And, And the mass in is equal to the mass out, or if it's plate, the heat generation is oxygen consumption. The energy out is given by this, and for the net heat is the total area that is not burning or is not the openings, the total area through which heat goes through, multiplied by the thermal conductivity of the structural walls, and you linearize conductive gradients, okay? Delta is the thickness of the wall, and this is the temperature difference. So basically, the equation, once taking all the terms that are necessary out, is this. And if you substitute the different values, you get the following expression, where effectively TF becomes the adiabatic flame temperature, and T conduction is a characteristic conduction temperature. So what you get is the evolution of the temperature of the compartment as a function of these two terms. So in essence, very simple equation that gives you the temperature of the compartment. Now, the interesting thing about this is that if you look at these terms, which are, if you look at it as T infinity, okay, TF, T conduction, okay, are the only terms in the equation, okay? And you look at TF is a constant, and a constant. So this is a constant value. So I don't have to worry about this. If you look at T conduction, it's a constant, a constant, a constant, a constant, and a constant. I don't have to worry about this. And this is the geometry of the compartment. So A is the areas through which the heat goes out. A0 is the area of the openings, and the square root of H0 is the height of the opening, okay? So if I'm an architect and I want to design a building, this is heaven, because all I need is the dimensions of the building, and then I know what the temperature is going to be, the maximum temperature is going to be in that compartment. So I can design buildings in a very straightforward manner, only knowing what the geometry is. Everything else is a constant. So in essence, this parameter is what you labeled as the ventilation factor. So this is the ventilation factor, and basically it's going to be the only parameter that controls the temperature of the compartment. So if you plotted the ventilation factor on the x-axis and the temperature increase on the y-axis, and you plot all of Kawagoe's data, you find out that the theory corresponds perfectly to regime 1, but as soon as your opening gets too big, then what happens is that the temperatures diverge from the theory. Okay? So this is the equation that I had here, okay, that for a very, very large opening factor is going to make this number very large, make this 10 to 0, 10 to 0. This becomes T1 and this becomes TF, adiabatic flame temperature. Okay? And for a ventilation factor that is very small, this approaches 0. So effectively, this number is very big, this number is very big. I can cancel the ones, the TCDs cancel, the TF cancels, and you get T infinity. So in essence, if you go very far, you go to T infinity. If you go, in theory, all the way till the end, you get to the adiabatic flame temperature. Okay? So in essence, that's the theory, and the data matches very well in regime 1, but in regime 2, it goes all over the place. What does Harmathy say? Hallelujah. This is brilliant, because in regime 2, all the temperatures are less. So the risk gets mitigated because this is a less onerous condition. So for these big compartments that we have in the US, we have a lot less of a problem than what the British have in their tiny little dingy rooms. Okay? So you can understand why nobody liked Harmathy. So in essence, you could do that, and then by doing heat transfer to the fuel, you can basically calculate the same thing for the burning rate. So now, if I know the ventilation factor, I know the temperature. And if I know the ventilation factor, I know the burning rate. And statistics tell me how much fuel I'm going to have. So effectively, I can construct a fire. And I can say that while it's burning, it will always be at TG max, a steady state, until total fuel consumption. And the total fuel consumption is the amount of fuel, a statistical variable collected by the insurance companies, divided by the burning rate that comes out from Kawagoe, that if you want to put it into an equation, is just simply this. And as you can see, it is also a function of the ventilation factor. Okay? So in essence, that gives me the time to burnout when I consume all the fuel. This is kilograms of fuel divided by kilograms per second. So this is the time that it takes to burn out the fire, and I can heat up at a constant temperature. Now, I can approximate a cooling function and say, well, yeah, it's cooling. That's not too big of a problem. Let's just simply make it a straight line that is representative of cooling in a fire, in a compartment that doesn't have a fire anymore. Okay? So that's the way you end up designing, and as you can see, ends up being an incredibly simple expression. Now, people have refined this, and you can use the data. So these are what we call the parametric curves, and instead of just using the maximum, the steady state, the peak value of the data, you can actually refine it by showing that actually the temperature increases, and there's only a short period where you get the peak. In Thomas, you will be treating this whole period as being the peak value, so it's conservative. So in the parametric curves, you're actually using the real data. But you can see the parameters are the same. It's still the ventilation factor, okay? So again, it is exactly the same thing. Now, you can go to real data and run an experiment and basically establish what your temperatures are going to be, the maximum values, the minimum values, or you can actually measure directly your heat fluxes. All these things we can do to try to refine it, but they start getting more and more and more complicated. So regime 2, basically we decided to ignore it because the data scatter was very large. You know, basically there's a lot of things that matter, and but at the end, the only thing that we should carry from this is that if we're not in regime 1, this doesn't work. Okay? So these relationships with the ventilation factor don't exist because they're only valid for the regime 1. So this is an example of what now has become quite well known, which is the concept of a traveling fire. So this is actually real data. So this is experimental data plotted as a function of time, and it shows you an experiment where you have a very large compartment, as you will get in modern buildings. And you will see that, that these fires can follow a series of different patterns. So in this case, for example, these are discrete elements of fuel that are basically igniting, and the fire is propagating across the compartment. This is not a regime 1, Okay? So this doesn't behave at all like regime 1. It's just a fire that is traveling around the compartment. So that's a traveling fire. Now, you can actually, under different conditions, get a growing fire, which is the transition between regime 2 to regime 1. Oops. So you can see how it starts here, and at the beginning is slowly creeping through the fuel, so it's traveling, but then eventually the smoke layer starts filling up the entire compartment and starts preheating the fuel, and then at some point you will start getting this instability, and it starts fluctuating, and eventually you get flashover and the entire compartment burns out. So again, this is a transition between regime 1 and regime 2. Now, if you want to see it physically, and if the video actually works, this is an experiment where you can see the transition. So this is regime 2, and you can see, how it's burning.
The cork?
And from the end of the wall to the middle where this column is, it took about 1 hour.
Cool.
So basically it's creeping along the timber that is burning in the ground,
Check if you can use camera
and
1
slowly
to
moving
direct it
across
there.
the compartment without growing at all. So this is just purely a traveling fire. Now, at some point, we changed the conditions. We basically put cork on the ceiling to reduce the area through which the heat goes through, and we brought it straight into regime 2. So by the time you get to the middle, we have forced this traveling fire to migrate into an area that now is regime 2. We changed the ventilation factor artificially to turn it into regime 2. Sorry, to turn it into regime 1, from regime 2 to regime 1.
Great, yeah. Use the word, yeah, 1 and 2, yeah, they're both.
Maybe I can.
Good.
Oh, I knew this was going to happen. Does anybody know why this happens? So let me put it straight to where I wanted to put it. So you see a transition. So effectively, let me put it a little bit before that.
Well,
yeah.
So as soon as it passes the column, you can see how the smoke layer starts building because you've ignited the ceiling. And now the area through which heat is lost is only the walls. And you see how the smoke layer descends, and you've moved from regime 2 to regime 1. So to be honest with you, if Harmathy would have seen this, he would have done the wave. Because in essence, this demonstrates sort of the different level of intensities of regime 2 with respect to regime 1 in a very, very large compartment. Okay, so you can see this is now back to a regime 1 fire, and you can see that again the flaming is outside, and inside you have a compartment that is filled up with black smoke, and the transfer of mass is only happening at the open. Okay, so it's purely hydrostatic. So through the years, people have been trying to improve this, and I got this from the Society of Fire Protection Engineers, and you will see, if you read the text, how as we progress, different researchers took this ventilation factor and the critical value of the ventilation factor as established by Thomas, and they started extending it. Margaret Law was the first one. Then you will see a little bit further, Magnusson and Terlander extended the range even further. And it keeps going. Different researchers keep doing this and basically keep playing with the range of validity of this ventilation factor for the regime 1. So people have been expanding this through the years, but in essence, the concepts remain the same. If you are not in regime 1, then you cannot use the ventilation factor. But if you are in regime 1, then you can have a very elegant solution to a very complicated problem, and that solution, while conservative, is actually really quite effective and is based on physical parameters. So a lot of people have played with this. So to summarize, this is an elegant framework that provides an answer to a fundamental questions. You state very clearly what your assumptions are. You state very clearly what your limitations are. And basically, you create a very simple design methodology that allows you to establish a temperature versus time curve that is actually physically based, as opposed to that weird standard temperature time curve that has no physical basis and is just a mathematical function. Okay? And the two of them are very different. So let's take a break, and then we'll do the final part of this. Okay?